So here, the target variable is donation. So the regression models will be logistic regression, and it will be selected. It will be automatically selected as logistic regression when you drag the regression node. SAS makes that decision based on the target variable, so you don't have to change it. I think before that, we need to do two things. One is the missing value imputation. For regression models, you need to impute the missing values in order to use those cases that has a missing for the particular variable you want to use. Another thing you need to use is standardizing the variables. So you know how to standardize a variable using z-score standardization. Now let's do the imputation here. So I think it's the first exercise on chapter 4, regression models. Regression. Okay. So if we take a look at the data set, so this one has a lot of missing values, but this is the rejected another target we're not using, so that would be fine. If you observe some of these variables, gift count, average, card, 36 months, you do see a substantial amount of missing values here. So to be able to use all the data points and still use this variable, it will be necessary to deal with the missing. Now we can exit. So the idea is to do a regression here, but before that we'll deal with the missing, and we'll deal with the standardization. The imputation will be under modify. Right. There's a default method that will be applied automatically to all the missing values depending on the type of variable. Let's see. For class variable, class input, which is nominal input variables, we would recommend a tree-based model, which will run a small decision tree in the back and try to predict the missing value, the best case scenario for the missing value, using a decision tree. So that would be better than, you did the homework. There are alternatives to replace the missing. You can throw it away, which is not good. You can use a fixed number, which is arbitrary. You can use a mean or mode, which is good, but sometimes it's not the most typical case. Median is always better than mean for interval variables, and a best approach would be imputation, right? So sort of model-based imputation. Using a tree would be a model-based imputation for the nominal variables. Right. Normalized values. Whether to use the normalized values. That should be fine. For the interval variables, the mean is the default method. at least for this, you would like to change it to median. Always that would be preferred for the interval. And after that, we need to specifically choose variables inside. Also, there's an option here to create indicator variable for any missing status. So what does that mean? And you can choose different types. You can choose single or unique. What it means, basically, the indicator variable is to document, using an additional variable to document whether or not imputation was done to a particular case. So if I'm one of the consumer in the data set, I don't have any missing values, then this additional variable for me will take a value of 0 because no missing was done to me. In alternative scenario, if I had a missing value, my age was missing in the data set, but then my age was imputed by one of the algorithms, then this additional variable, indicator variable, for me would be 1. That means I originally had a missing value, but then the missing value was imputed by some kind of algorithm. So this indicates the status of missing originally, right? Why is that important? Because sometimes knowing that the information is missing for a particular case is by itself informative. If the missing trend is systematic, right? This depends on the context then. So let's see, if I do a consumer purchase study and I want to predict the likelihood of purchase, then I do a survey, ask people about their income. And then low income people will be reluctant to indicate the income, maybe. And then I will have a missing value for that, for those part of the respondents. And then the missing status itself may indicate that they have a lower likelihood of purchasing because of lower income. So that's one example. So this gives you some additional ways to model the relationship between the missing status and the target. So this creates this possibility. If you say none, then nothing will be created. If you choose one of these, then additional variables will be created. The single one means only one missing indicator will be created for any number of missing imputations done. The other is simply to create one additional for every additional imputation that's done. So this is something to know. So this might be something that you should try when you do the projects, when you do the group project or single project, when you have done all the standard models, but you want to creatively make some more additional models. This is something you can try, right? To create additional variable and see if that, increase the performance of the model. I think that's it. So by simply doing this, it helps you to use additional cases from the data where there were missing values. After the imputation, you can use those cases. Only 2 variables had missing values. After imputation, the original variables were rejected, right? And the new variable has this label. both of them are interval variables, so the median was used to replace the missing. So that's the result. Then you also need to standardize, and standardization is in transform variable node, right? If you remember, to do standardization, you will use the transform variable node. The tutorial also talked about log transformation. That is something unique. Log transformation fixes the skewness, as I talked about in second class. It removes the skewness to some extent, and may help you, may help regression model better capture the linear relationship. But sometimes it may worsen the model because the nature of the relationship the linear relationship was really on the original scale, but not on the logged scale. So when you log transform the variable, the linear relationship may decrease. So it's a mixed story. It doesn't guarantee you any better. Log transformation is recommended for statistical analysis, just because log transformation evens out the error distributions, and it helps the data better conform to the assumption of the regression. But so that's for statistical purposes. But we're dealing with prediction. Anything that improves the model, prediction would be better. So, the utility of log transformation is mixed. I can't recommend it. I can't say no. So you need to try, right? To log transform variables, it's the same place where you do the standardization, right? It's the transform variable node. So I won't do it here. I'll simply do two regression models. So I'll do a forward selection. Let's see. Or maybe I do a full regression where I include all the input, and then I do another stepwise regression which has some variable selection mechanisms. So this is full regression. Main effects, two factor. You can also add polynomial terms, but I will not do it here. This is somewhere you can try to explore additional models and try to improve the performance. And it says regression here because it detected. And sometimes even if your target variable is interval, like say, price, sales price, and when you do the regression, it shows logistic regression. Don't worry, it will not misapply the type of regression. It's simply because it didn't run or maybe it didn't update. But back in the analysis, it will use the right type of regression. Suppress intercept, no. Selection, model selection, variable selection mechanism. For this one, I'm not using any selection. I'm using the full regression model. Let's see. So that's that's a full regression. Another regression with some selection. In stepwise regression, I would choose model selection to stepwise, and keep all the other selections. And in this case, I will link it to model comparison, yeah, and compare all the models together. So in this case, the stepwise regression seems to perform better when it uses a combination of forward and backward selection. So this mechanism help it to retain the most important variables and remove least important variables. So in this case, see if your results will be similar to mine. Full regression is even worse than the maximal tree. So if your best classification tree had a better result, then the full regression would be the worst model here in terms of validation misclassification rate. So the full regression, it does harm the prediction of the model by including everything in it. So you want to have some selection mechanism to avoid including everything in it, right? Because this data set does have 30 plus variables. It's quite a long list of variables. make sure you have the same rows selected as shown here, as well as the label, the level, not label.
Does the level matter for the rejected ones?
Yeah. So make sure you have both fiber and sugar as input here. And later I'll show you how to reject one of them during one of the later nodes, that you don't have to reject them before front, or you don't have to need two data sources in order to, use different sets of variables. Are you good? We move on? 1 second, okay. It's converting the data set takes some time. Can you not see clearly? Do you need a magnify? Do you need enlarged if it helps? No, yeah. That helps? Yes. Great. Well, just so you know, this is recorded, so you don't have to think about too much about future. Future is taken care of. It's only now. Okay? Everybody's good? Great. So at the end of the day, you will have 2 input, 1 ID, and 1 target. The ID is not super critical, but it's better to have one if you have. Okay. Now. Move on. Confirm that you have 77 rows. Okay, we need a new diagram. Okay. So the project is prepared. Now the first thing, as always, would be to explore the data set, to look at the missing values. And the first thing I need to change is for it to also include the interval variables. And you know, because I know this data set, there is some missing value in it, but other than that, there is not much unexpected. So I will continue to add another node. So in this case, typically, so regression is still a supervised learning method, and to make a good prediction model, you need cross-validation, right? For the homework, to get the same results, to get the results that are expected, I hope you keep everything in the same sample. So then you will not need data partition just for the homework, but otherwise, for project-wise, you need it, right? So I don't need to use a data partition, and because I know there's a missing value here, so I will need an imputation node that would be modified. And if you are familiar with your data set, supposedly, you know that you have done exploratory analysis, you have understood the missing value situations, you have a pretty good understanding about the variables and what variables have missing values, and you know other peripheral information about those cases that have missing values, then you can use a default method for you to automatically impute missing values depending on the type of variable. Here, the class variable setting, property setting, will not make an impact because we don't have any nominal variables here. Only the interval variable method will make a difference. And as I emphasized, interval variables may have skewed the distributions, and compared to mean, median would be almost always a preferred method to impute the missing values. So I would do you would do median, and by this point, I think you can run it so that it runs all three nodes. So examine the results of impute. Make sure something is that missing values are taken care of. Sugar, seven missing values have been modified. What now? 7 is the replacement. So 7 is the median for sugar, I think. Number of missing cases in training is 1. And there's only one set of data, which is the training set. And to go back retrospectively to look at the results of the stat explore. There are 2 interval input variables. There are no class variables here. there is one missing value in sugars originally. The median value is 7, so the replacement value is actually the median. If you take a look at the correlation of the two input variables with the target, you see that they are fairly correlated. The less correlated one is fiber. Correlation is 0.58. The more strongly correlated is the sugar one, and the correlation is negative, which is, reasonable. Nowadays we hate sugar. Sugar is the evil.
That's the correlation between that variable
with the target.
rating, right?
With the target, yeah, with the rating. And for regression modeling, there is an optional data transformation step that you may or may not do, or you may use to your advantage to diversify your model in hope of searching for a better predictive model. So the reason why you would use log transformation, log transformation is to fix the skewness of the distribution. As with other alternatives, you can do square root as well, or reversed square root as well, as the textbook talked about. But log transformation is a more commonly used technique, and it fixes most of the problem, if not all of them. So it's adequate if you use it. The reason why you need it sometimes is because it lessens the impact that outliers may have on the model. If you have a long tail in some of the input values, then log transformation may help you increase the model performance. But it's not always the case. And sometimes your target variable may also have skewed distributions, and that complicates things. So the bottom line is that there's no absolutely right way to make a judgment. You need to think about what really may help you capture the underlying trend. Does the variables at their original scale will help you capture the linear relationship between the input and the target? Do you believe that the relationship between target and input on their original scale should be linear, relatively linear? When the input is very large, which is in the tail, which is an outlier, do you think that it exerts a similar linear effect on the target? If that's the case, then you may be better off not log transforming the variables. But if it's not the case, then you may be better off to use log transformation. A simple example to illustrate both cases is that, let's say, if you're modeling bidding price of a buyer on a property, and you are using the income as the input. So another way of saying the model is that you're using income as an input to predict asking price, not asking price, bidding price, or your offer price, right? Then you would expect that the higher the income, the higher the price that the buyer is willing to offer. And the relationship might be very linear on their original scale. So you might be better off not taking the log. Taking the log will remove the specialty of this case, which is the high income affluent populations. So which may adversely impact your model performance. But say another case where you're predicting grades with socioeconomic status, like, household income, parents' education, things like that, then there is a non-trivial segment of the population, maybe 15% of the population, who have higher income than normal. Their family income are in the outliers, but the grades are typically, quite symmetric and well behaved and normal. So you have a natural ceiling for the grade. You can be as good as 4. You cannot exceed 4.0, right? So in that case, the income as being, family income as being an outlier doesn't contribute too much linearly to the grades. The grades have a ceiling effect. You cannot exceed that, right? Because grades are something that is more arbitrary than other things. So in that case, you may wish to sort of to contain the impact, the excessive impact of income outlier effect on the grades. So these two cases are quite different on the target, but similar on the input side. So you can make different decisions and rationalize. But in the end of the day, hopefully you will look at both, and to see which model, a model that doesn't use log transformation, the other uses. You can compare them by using cross-validation, right? And select the model that predicts well. Does that make sense? Yeah. So here I'm just going to demonstrate how to do log transformation, and we'll interpret the results with log transformation incorporated. This doesn't mean that I, recommend using it all the time. You need to make the judgment and to rationalize the decision. So, can you tell me which node has the log transformation technique? Transform variables. Very good. So it would be under modify. And for this case, because you only have 2 interval variables, then you can use a default method. For interval inputs, you can choose to use log or log 10. And with everything else as known and not changed. So I won't run it for now because, I'll build the regression model and then run it at the same time, so to save some time. So the first, there are 2 questions in homework. The first regression model that the question asks you to build is the simple linear regression that involves fiber, I think. Right? So, and up till this point, you have both input variables included. And then model, regression model. And this is a simple linear regression. Let me rename the node to make it clear. And here you can customize the specific variables to be included as input. In other words, you can wait. Okay, yeah, I haven't log transformed. I was looking for the log prefix. I didn't see it because I haven't run it, but that's fine. Well, you know what? I think that may matter. So it's better to run it first. Review the results. Logged version of the variables are created. Each of the original variable is the algorithm added an arbitrary 1 to the original variable and take the log. Right. So then let's update the path. Now, I think we will see the updated variables. So now we have two logged version of the inputs. For simple linear regression, I will only keep the fiber. So I will change for the sugar to be no, which is great. Now, simple linear regression would not have these features available to them. Even if you do, it don't make a difference. And given a reasonable correlation between the input and the target, you will find this model to be significant. So up to now, I think you can run it. So review the results. This is a table that you see a lot. This is the mostly the model evaluation, as well as some other diagnostic measures. You have average square error, misclassification rates, standard list of metrics. This output window will be the one I'll focus on. Here, it looks something like the like score ranking chart and things like that, which we'll talk about in the model evaluation chapter. This is plotting the sides of the coefficient. Okay, the regression output sometimes can be very long. If you do a stepwise regression, then there are multiple steps, stacked above each other. And then if you have 10 steps, then you have 10 sections, and maybe more than 10 sections of the output. So sometimes it takes a little trick to get around these outputs. And there is search function here, so you can. So if you know the keyword for the section that you want to look for, then use the search function. So the question here is several key statistics that you're looking for is R squared and adjusted R squared and coefficients, and along with the list of variables. For R squared, you can see that it's 0.3, close to 0.3. It's not super good. It's not minimal as well, and which reflects the correlation, the level of correlation between fiber and rating. Right. And then to interpret, the question in the homework asks you to interpret, what does it mean by the coefficient of fiber or log fiber, right? In this case, it's a logged version of fiber. The coefficient is 11.4, close to 11.4. What does it mean? And for this simple linear regression case, you would interpret that for each for each unit of increase in logged fiber, the estimated or the average log rating. This time, is it log rating? Did we log transform the target? No. So it's the original rating. The expected or estimated value of rating will increase by 11.4 points. That's if the rating is in the original scale. That looks reasonable, because if I did the log transformation and the scale, the maximum would be at best 5. So the coefficient won't exceed 2 typically. Right? And this intercept indicates that it's way more than 5, the average rating. So rating was not log transformed. So that's the interpretation for the coefficient. Is that clear? Great. We can move on. Next question asks you to build another regression, which is multiple regression that includes additionally sugar. So in this case, you can modify that regression. Then you need to do multiple things, or you can bring in another node, which is another regression model, which I think is easier in this case. I would also rename that regression model just to be clear. And in this case, I won't reject any other variables, so I will keep them as default, and then both input variables will be included. Also, I will not select any stepwise regression models, just because I expect both variables to be significant to contribute to the model, and even if I select it stepwise, neither of the variables will be rejected or will be excluded. But of course you can try, but the results might be the same. And also, just to make a note, here rating is continuous, right? Rating is interval. So for a regression model that works for an interval target, it would be regular regression, linear regression, instead of stepwise regression. But if you take a look at here, this model has already been run. It still is designated as logistic regression. This is, of course, not the case in terms of the actual model that's used by SAS. But SAS was just lazy, I think. SAS didn't change the label, but in fact, it's not logistic regression. It's linear regression. So, you don't really have to care for it. But if you are a perfectionist, you can change it if you prefer, which won't make any other impact. And that's it, and you can run it. So same layout. Now you have three variables, including the intercept. Even though you have only 2 inputs, but you do have an intercept, which is typically the highest in this case, in this homework. Now, first thing to look at is to confirm both variables are included and coefficients are calculated. And you notice that R squared changed quite a bit. Do you recall the R squared before? 0.29 something. Good memory. Close to 0.3, but now it's 0.85, close to 0.85, which is a significant jump. And there isn't too much of a difference between R squared and adjusted R squared, which means that both of the variables contributed meaningfully to the to the regression model, basically. And now, if I ask you to interpret the coefficient of sugar after the transformation, how would you do? Right? For each and every unit of increase in transformed sugar, and holding everything else unchanged, because now you have two variables, right? The other variable, if there was some change, the coefficient would change for fiber. I mean, there's a fiber, so if fiber changed, then coefficient for sugar would also change. Now, the third part is estimated or average value of rating is expected to drop 13.67 points, right? Anybody recall the coefficient for fiber previously in the simple linear regression? Huh?
I think 11 point something.
11 point something, yeah. So now it changed. It dropped to 9 point something. So that's why the additional clause, the additional statement that says holding everything else unchanged is important here. You know, to be scientific in interpreting the regression results. And if I ask you to write the equation of the regression model after by using these coefficient results, how would you do? In this case, for multiple regression case, you know, you'll write an equation. There's a left-hand side, there's a right-hand side, right? The left-hand side is the target. So, you know, put the name of the target there. Don't simply write target. It's reasonable, right? So whatever is the target here, it's rating. The right-hand side will include the intercept and the additional two terms, which is the coefficient multiplied by whatever the input is that the coefficient is for. Make sense? I think you, out of all the models, you have most experience with the regression, so I don't necessarily need to demonstrate everything. That's it for the leftover about regression. Any other questions? Yeah, simple enough. Okay. Yeah.
So for this, I kind of played around with the homework earlier today. I didn't do a log transform. How would we have known that might have been a good idea, that just good practice? You can compare the model performances, and if the objective of the project is to have the best predicted model, then, you know, under the cross-validation framework, you can compare two models, one that uses log transformation, the other that didn't use, but make sure that you do the same with the target variable, right? You can't log transform one target, but didn't log transform the other target. You can't compare them because the target is different, all right? You know, keeping the same operation on the target but varies the operation on the input, you can see the result, right? Make sense? Yeah. Typically, regression is used to explain the phenomenons. So that's within the explanatory regime of data analysis. And in that regime, people don't care really that much about out-of-sample predictions. In-sample prediction is what they care, because they try to explain everything that is
that can be explainable in the training set. So in that case, you won't have cross-validation, but then everything else would be similar. So in the explanatory data analysis regime, then you would simply compare two models on their R-squared. Then you can say, you know, the one model that has the better R-squared is whatever the model that you preferred in terms of log transformation. Yeah. Any other questions?